our surface area problems we'll take a look at. We'll try to hammer out that process and get it to be more or less intuitive. So we are sitting at this slide here. So we're going to rotate the curve that we have up there. It's part, it doesn't even matter. The function is right here. Looks like it's part of a circle. It may or may not be, depending on what's going on. Looks like a shifted circle. Doesn't really matter, but this is the equation for that arc right there, and we're told that we're going to look from 1 to 4. We're going to rotate around the x-axis, so we're going to get this kind of sphere-looking thing with the caps cut off, the North Pole and the South Pole cut off. So we're going to get that belt. And the finding of surface area is very procedural. We have this formula that we're going to use, and it's 2 pi r, and that is circumference, so that's how I would remember it. The idea with your surface of revolution is that if you take a cross-section is a circle, right? So if you have a surface, not a solid, just the surface, and you take a cross-section, you're going to end up with a circle. So if you rotate that point right there around the x-axis, you get a circle. 2 pi r is the circumference of that circle. And then ds adds a little height to it, a little thickness, a slant height. And that's what turns it into the base of a cone, into a frustum. So that's the idea. So that's the concept right there, is that you have a circumference, that's the cross-section, add the ds, and that creates what we normally would call a slice, but intuitively when we think of slice, we think of more of a solid. But when we do the ds, that's adding thickness that creates the little cone base, the frustum. So it's all very mechanical. So we know that with the ds, we have to find y prime and then square it and then add 1. So we have our ds formula that we learned from the arc length section. So we're just doing that for ds. So it's arc length multiplied by 2 pi r. So y prime, in this case, will bring down the 1/2. So that's to a half power. The base is going to stay the same. And then we subtract 1 from the exponent. And then we apply the chain rule. The chain rule says that if your base is not just x, you need to then multiply by the derivative of the base. So that right there is our derivative. That's y prime. And we know that we need to then square it. So we're going to square this. The middle factor here is a square root that lives in the denominator. Right? A negative half power is a square root down below. So when we square it, this is how I'll write it. I'll write this part in the numerator, that 1/2 is in the 2 is in the denominator, so when it's squared, it's going to become a 4. And this square root, when it's squared, the square root just vanishes. So there is our derivative squared. And then we have to add 1 and take the square root and put it into the integral. So let's see. So our surface area, we'll use a capital S. 2 pi r, the 2 pi can come out to the front of the integral because it's a constant. We're told that we're integrating from 1 to 4. And r, right there, r is the function. Right? That's what the function measures. It measures the distance from the curve to the axis of rotation. So that function gets tossed in there. There's the radius. And then that gets multiplied by the square root of 1 plus the derivative squared. Well, we already did that right in front of us, right here. So I'm just going to put this in. And then dx. And the numerator, we're going to have to FOIL that out. That's going to be 25 minus 20x plus 4x to the 2. So there is our seemingly miserable integral. Questions, Scott? No. That one. Sorry. You have a look like you were not convinced on something.
I just missed it too.
Okay. Everyone see the foiling? So now here we go back to algebra, and we have to remember that if you have the square root of a multiplied by the square root of b, that turns into a single square root, and we just combine the insides. So we multiply the two insides together. And another way to think about that is that the inside of this square root is going to distribute. So we can multiply the inside of that root by both fractions in the second square root. And that's a good way to think about it because we see that the 5x minus x squared is going to cancel in the second fraction. We have a common factor there that's going to wipe out. So that'll simplify tremendously. So when we combine our two, we will have one big square root, 5x minus x squared times 1 gives us that. And then 5x minus x squared times the second fraction, this will cancel, and we'll be left with the polynomial in the numerator divided by 4. So I'm just going to divide that 4 into the numerator. And we end up with that. So we took the inside of the first root, distributed it to the inside of the second root. We're going to get a cancellation. If you need to, remember this is over 1 if you want to put that there. So that 5x minus x squared and that one down there, one's in top, one's in bottom, they cancel. Now we have a bunch of cancellation in here, right? So what we see is that the 5x is going to cancel with the minus 5x. And we're going to get the x squared and the minus x squared. Those cancel. We love it when that much stuff cancels. So the only thing left is 25 over 4 inside of a square root. Square root of 25/4 is 5/2. That's a constant. It comes to the front. And we're just left with the integral of dx from 1 to 4. And what is the value of the integral of dx from 1 to 4? 3. Upper minus lower. 4 minus 1. 3. So we end up with 5 pi, simplifying this stuff out in front, multiplied by 3, which will give us total area of 15 pi. So the surface area one's very procedural. We just sort of have to deal with lots of algebra usually. Any step there that you are curious about? Yes?
How did you get the square root of 1 plus 25 minus 20x?
This?
Yeah.
So that's 1 plus the derivative squared. So here's the derivative squared. And then we add 1 to it. So the numerator, we FOIL it out, 25 plus 4x squared, and then minus 2. You see it?
Okay.
All right. Foiling. Any other ones on there? All right, let's try another one. So these surface area ones, you sort of try to, it's a lot about bookkeeping. It's a lot about trying to just keep everything straight. So let's take a look at this one. Now this one, they're trying to trick us. Let me point out a couple of things that lead me to say that. So first off, they say we're going to rotate around the y-axis. But they haven't given us a function of y. They've given us a function of x. So normally what we've been doing is if we have a function of x, it's been going around the x-axis, and a function of y is going around the y-axis. That tends to be the simplest way to do this, is that if you're going to go around the y-axis, you want a function of y. If you're going to go around the x-axis, you want a function of x. So this one is backwards. They're commingling here. So what we want to do is take this function here, and we're going to want to rewrite it as an x value so that we can then have a function of y that's going around the y-axis. So that's going to be a good rule of thumb with arc length, with surface area, is that if you're going around x, you want a function of x. If you're going around y, you want a function of y. So that's not too hard to solve. So we'll have 4y equals x squared. Solving for x, we're going to get x equals plus or minus 2 times the square root of y. So this is a parabola, and we can kind of see that this parabola goes right through the origin, and it's this direction. So are we going to choose the positive x value or the negative x value for that portion of the parabola? That's the positive x values, because the parabola would come over here. This side would be the negative x values over here. So we have the curve x equals 2 times the positive square root of y. And that is now the radius. Right? This curve, written as an x value, is measuring the distance from the axis of rotation over to the curve. So that is now the radius. So this is the radius. All right, so now we have our function. So we come over here. We've got our function, 2y to the 1/2. We need its derivative. So our formula is going to have an x prime squared instead of a y prime squared like the last one. So we take the derivative here. We get y to the negative 1/2. The square of that is the next step. Square of that is 1 over y. Because again, a half power is a square root. A negative half power is a square root in the basement. And then we square that, and we'll get 1 over y. So now we're good to kind of set up the whole integral. So the surface area is the integral from, let's see, we have a horizontal element. So are we integrating with respect to y or x? We're going to integrate with respect to y. So these limits of integration need to be y limits of integration. They've given us x limits of integration. To get the y limits, we just plug the x values in right here and get the corresponding y values. So y will end up being between 1. Let's use a different color. So y will end up being between 1 and 4. Let's see if we can convince ourselves of that. So if you plug in x equals 2, 2 squared is 4, 4 divided by 4 is 1. That's that y value. This over here, you plug in 4, 16 divided by 4 is 4, so you get your y values are between 4 and 1. So those are our limits of integration from the y-axis. We're integrating with respect to y. And then we have our 2 pi times the radius. So this x value right here is measuring the radius. So that's 2 times square root of y. That's the radius. That is this x right here. So notice in this formula here, this is the radius. We can't have an x and a y, which is one of the clues that we need to convert this over and have it written in terms of y. And now we throw in our other square root. So we have 1 plus x prime squared. So 1 plus x prime squared inside the square root. So there's our setup. Any step in that setup that you want to ask about? Mm-hmm.
Would we ever use the negative 2y squared, or is that just a byproduct?
An extraneous. Yeah, in this case, no. But if they drew the graph over here, if the curve that we were going to rotate around the y-axis was this side of the parabola, then we would choose the negative instead of the positive.
Right.
So it all just kind of depends on how they present the curve to us.
What if you're not given a curve? Would you be given a different equation?
Well, they're gonna, if they don't graph it for us, up here they give us the curve. They have to give us the curve that we're going to rotate. And so then if we're going to change the perspective, so here they gave it to us as a y value. If we're going to rotate around the y-axis, we want to write this as an x value, then we'd have to do some manipulation. And when we do that manipulation with a quadratic, we're always going to get that plus or minus. So then we have to just look and decide, are we choosing the positive x value side or the negative x value side? So somehow they're going to give us a curve. They might not graph it for us.
Okay.
but we would have to then graph it and figure out which portion of the curve is the side that we're interested in. Yeah, but they will give us the curve. Once again, we have two square roots that are being combined with multiplication. So all we do is share the inside of the left root with the inside of the right root. And that is easily integrable. We can do y plus 1 to the 3/2 multiplied by 2/3. What kind of function is this inside the root? Is that a trig function? Is it quadratic? Is it linear? It's a linear function. So that means we can use the reverse chain rule. So we can just do this, the integration as we see it. Oh, we have a square root. We add 1 to the exponent, divide by the new exponent. Now the coefficient of y is just 1, so there's a little bit of reverse chain rule that we don't really see. What if this was a 3 in front right there? What would be one other thing we would have to do then? So we'd have to either multiply by 1/3 or divide by 3 if there was a coefficient there. So we don't see the reverse chain rule in action here just because that coefficient is 1. But if it wasn't, we would do that. So we have an 8π3 up in front. We plug in the 4. 4 plus 1 is 5. 5 to the 3/2. Usually we write those 3/2 powers like that. 5 to the 3/2. That's the square root of 5 times the square root of 5 times the square root of 5. 2 of those square roots of 5 turns into a 5 without a square root. And then we plug in the 1. So 1 plus 1 is 2. We have square root of 2 cubed. And again, we usually will write that this way. And we have a 3/2 power. All right, any piece of that you're not sure about? You know where all those letters come from? Good? All right, let's do another one. So this one, here everything is in alignment. They say we're going to wrap around the y-axis, and they give us a function of y. So that matches, right? They've given our function, they've presented it as an x value, so that's measuring horizontally, and that's what we want with this. When you look at our picture here, that when we rotate this around, if we're going to rotate around y, that radial distance is a horizontal distance. So that means we want the function written as an x value to measure horizontal distance. So in that one, we had to convert it, but in this one, how did I get there? So with this one, they've written it as an x value, and we're going around the y-axis, so that all is fine, right? That's copacetic. So we know we need, here's our formula, 2πr, there's the circumference. And when we have the function written in the right form, the function is the radius. And then we need the ds, and ds is the 1 plus either y prime squared or 1 plus x prime squared under a square root. In this case, we have a function of y, so we're going to do an x prime. So our x prime, we'll pull the 1/2 down. We'll leave the base alone. We'll subtract 1. And then the chain rule says multiply by the derivative of the base. So there is our x prime. Then we have to square this. So very similar to the last one, this is a square root that's in the denominator, and when we square the square root, they cancel each other out. Before I square the other stuff, one thing I notice is that a 2 goes into 2 once, and we can divide that 2 into the numerator right there. So we can simplify that to 6 minus y. And now we're going to square the 6 minus y. And let's just write it as 6 minus y squared for the moment. So that'll be the derivative squared. Question?
Just don't understand what you do with 1/2 there.
This 2 is in the denominator.
Yep.
This is in the numerator.
Yep.
And so I took the 2 and I divided it into this factor.
You don't have to do it. Oh, never mind. It's
You see it?
-1. Yep, -1.
Yeah, so if you have something like 4x over 2, you just divide it into 1 if it's multiplication. You don't distribute it. So now let's build our big integral for surface area. We are going to integrate from 2 to 10. They give it to us. And then we have 2 pi r. 2 pi r, the function, again, is r. The function is measuring the distance from the axis of rotation. So that's going to be square root 12y minus y squared. That's 2 pi r. And now we put in our ds. ds is the square root of 1 plus the derivative squared. And I am going to FOIL this out now. Make that 36 minus 12y plus y squared. And that's all divided by 12y minus y squared dy. So that is the ds. And just like the last couple, we have a pair of square roots that are being multiplied. To simplify, you take the inside of the left square root, and we're going to share that with the other square root. So it's going to distribute to the 1, and it's going to distribute to this second fraction. And the nice thing about that second fraction is that we get a cancellation with the denominator. So that's going to really clean it up quickly. So we'll have square root 12y minus y squared times 1 is that. 12y minus y squared times 1. And then when we multiply it by the second fraction, we end up with just the numerator because the denominator cancels. And we can see that there is some nice cancellation. Negative y squared, positive y squared, positive 12y, negative 12y. So once again, we get a really nice simplification. So we're going to have 2 pi times the square root of 36, which is 6. And now our integral is 2 to 10 dy. And what is the evaluation of integral 2 to 10 dy? 8. It's the upper limit of integration minus the lower limit of integration. When you integrate a differential, you get the length of the interval. So we are going to end up with, what's that, 12 times 8? 12 times 8 is 96 times pi. Lots of algebra. All that square root stuff you hope to never see again. Okay, tedious algebra. One more tedious algebra question, I think. So same idea. They just throw in a few extra words and they turn it into a, kind of application light. So they talk about this arc right here. We're going to rotate it about the x-axis. We're going to create, something similar to what we've already seen, a sphere with the 2 caps cut off. And they want to, make it application light by saying we're trying to find the volume of the paint needed to paint this surface. So bottom line is we're still doing what we've been doing for the last few examples. We're finding the area of a surface. But to answer the application piece of it, to find volume, we're going to multiply by 0.0015 at the end because we want to have the paint is 1.5 millimeters thick. So not really a hardcore application, but still have to do surface area. Now, one thing that we notice is that we certainly have some symmetry. This is -8 here. This is +8 here. So we have this arc that's symmetric about the y-axis. We're going to rotate about the x-axis. So we could do a symmetry thing and multiply by 2 and have our limits go 0 to 8. We also want to make sure that things are in alignment. So if we're going to go around the x-axis, we want to write this curve as a function of x. We want it to be presented as a y value because it's got to measure this vertical distance right here. So when we write the equation for that curve, that's going to be y equals, subtract off the x's and take the square root. We're going to get y equals plus or minus 100 minus x squared. And do we choose the positive or negative? Positive. So if they had given us the curve down below, the bowl part, if they had said, let's use the lower half, then we would choose the negative one. But they've given us a portion of this circle that is above the x-axis, so that is going to be the equation for the curve right there that we're using. So it's the upper semicircle. And then we do what we've been doing. We have to find ds. So we're going to find y prime. Y prime, we do what we've been doing. We bring down the half, subtract 1, multiply by the derivative of the base. So standard chain rule. And then we want to square the y prime so that we can put it into the square root thing. And we notice that there is a cancellation. This 2 is in the denominator. This 2 is in the numerator, so those can cancel. And when we do our squaring, the only piece left in the numerator is -x, and that squared will be x squared. And in the denominator, we have a square root, which will then cancel with the squaring. So there's our y prime squared. So our big ol' integral is going to be, let's put a 2 out here for symmetry. That's because instead of going from -8 to 8, we are going to choose to go from 0 to 8. And then we have our 2 pi times the radius. So this curve, when it rotates around the x-axis, here is our representative point that's being wrapped around the x-axis. So we need that distance. Well, that's what the function does. So there is the radius right there. The function measures that distance to the x-axis. So there's the 2 pi r. And now we have to multiply by ds. ds, we know very well now that that's the square root of 1 plus y prime squared. So that will be our full setup then. And our symmetry, we are just looking at this part 0 to 8. So we're going to go on that interval, 0 to 8. Or you could go -8 to 0 and double it also. That would work. So the simplification, same as it was in the last couple. We can pull our constants to the front. We have a pair of square roots. They're going to combine. So we combine the insides. In other words, a good way to think of it is that you can take this quantity and distribute it to both terms in the other square root. So when we take that 100 minus x squared, we distribute it to 1. we end up with 100 minus x squared. And what are we left with when we distribute it to the second fraction? Yeah, just x squared. And we get more cancellation. These have been cooked up very nicely for us. So we have a minus x squared and a plus x squared. Those go away. Square root of 100 is 10. 10 times 4 is 40. So we have 40 pi. Integral 0 to 8 dx. And what's the integral of 0 to 8 dx? 8. Upper limit minus lower limit. Anytime we integrate a differential, that just means the length of the interval. So we are going to end up with 8 times 4, so 32 times 10 times pi. And that's it. That will be the surface area. So that is the first part. Now they did the application thing here. So to finish it off, the volume will be 0.0015 multiplied by this. So type that into your calculator, and whatever they say to round it to, we would round it to. Do they
0.48 meters cubed, or pi meters cubed.
Did you say 7.48?
0.48
0.48
pi meters cubed.
meters cubed. Thank you. All right, any question on surface area? Is there anything about surface area that's not making sense that you're... The concept of taking 2 pi r and multiplying by ds, is that making sense? So the idea is that we always are looking for approximating shapes. So we're taking those little frustums to use those as our approximating shape. And then this is the area of a small frustum. So this right here is a frustum that's very small. Right? The ds makes it very small. 2 pi r ds. Circumference times slant height. You get to do a little bit of physics.
No.
A little bit. We'll approach it from a very mathy point of view. We're going to be more like we're going to treat it in as basic a way as possible. No highfalutin physics. Some of you can probably throw in some extra physics as we go through this stuff. So we're going to look at basic concepts. We're going to be dealing with force. We're going to be dealing with work. And force, work, and is there one other thing I think? That's all I can think of right now. We're going to be dealing with at least force and work. So force and work. Oh, mass. Mass is the other thing. So let's take a look at some ideas. So first off, density. When you all think of density, you are thinking of a solid object and you're thinking about mass per unit volume. That's kind of the density that we're all familiar with. But what we have to also keep in mind is that we can talk about, and that's what I would refer to as three-dimensional density. So if we're dealing with a solid object, we're thinking of three-dimensional density. We're thinking of mass per unit, per unit volume. So if you have something that's super flat and thin, you could talk about mass per unit area instead of mass per unit volume, and that would be a 2D density problem. So if you have a sheet of metal, and it's super thin, we're going to think of that as a two-dimensional problem. So we'll do mass per square unit instead of mass per cubic unit. And moreover, you can even go all the way down to like a wire where you have a one-dimensional density setup, and we would talk about kilograms per meter or something like that. We would talk about mass per unit length instead of mass per unit area or mass per unit volume. So we're going to have three different types. Now in this class, well, first off, if you want to get mass and your density is not uniform, that's where you have to integrate. So if you have an object, whether it's solid or a plane, a region, or whether it's a wire, if that density is not constant, you can't use our basic formula that, that mass divided by volume gives density. You can't use that if there's a variable density situation. So in that case, that's when we integrate. Now, we don't know how to do a double integral or a triple integral. So if we are going to integrate density, it is going to be for a one-dimensional setup. Because to integrate, if you're doing a two-dimensional setup, it would take a double integral. If you're doing a three-dimensional setup, so if you have a solid and you've got variable density, you would have to do a triple integral. So those two cases will be left for Calc 3, where you're doing calculus in three-dimensional space. So for us, the simplest case, where we're talking about one-dimensional density, we just integrate the density with respect to x, and that's going to give us the mass. So we are thinking of the very special case where we're dealing with a wire or a rod, and we know the density function that tells us the density at every point along the wire or the rod. All we do is integrate with respect to x, and that gives us our mass. So this part, this will not be on the test, this piece. This is more just concept building to get to where we're going. So here we've got these two density functions. We're talking about and we are told that we're dealing with a very thin bar, so like a rod or a wire type thing. All we have to do is integrate to get mass. So these two problems are strictly to get us into the concept thinking. Integral of density gives mass. These obviously are not challenging problems. So we integrate. The ones that will be challenging will be when you get into Calc 3 and you have a two-dimensional setup or a three-dimensional setup. That's where this is all going to go. So this part here, we've got that. They don't even give us units on this one. So this is going to be the mass. Typically, it would be kilograms or grams, one or the other. But basic concept, you integrate density to get mass. And if the density is variable, that is when you are absolutely necessarily going to use an integral. So same idea here. We're given the density. It's a variable function. So that means we have to integrate to figure out what the total mass is. We have an exponential. What kind of function is this in the numerator, in the exponent? Linear. So if it's linear, we go, reverse chain rule. So we're going to use an RCR there. So this tells us that we're going to end up with 5 e to the negative 2x. So the integral of an exponential is itself, first and foremost, itself, any exponential. And then we do what for RCR? Divide by negative 2. Nothing crazy. Okay, so then this gives us negative 5/2. I'll choose that as the coefficient. And then we're going to get e to the negative 8 minus e to the 0. E to the 0, of course, is 1. So that is our mass of the wire, the rod, this one-dimensional object. Is mass positive or negative? Is that number positive? It isn't?
No, it is because of the fraction.
Yeah.
The negative number.
Right. This is a super tiny number, right? Less than 1 in magnitude. So this part's negative and this part's negative. So if you wanted to, you could rewrite it so it doesn't look so, it kind of looks like it wants to be negative, right? You could rewrite it like that. And that e to the negative 8 is super tiny, so it's going to remain. That's going to keep us in the positive side. Okay, so basic concept. Integral of density is going to give us mass. All right, let's go to work next. So the basic concept is that work is force times distance. So force is either going to be measured in pounds if we're in the empirical system. What do we call that system? I don't even know. What system?
Imperial?
Isn't that one the?
No, it's metric and imperial.
Metric and imperial. So imperial is pounds.
Yeah.
And newtons will be in the metric system. If we have a constant force and the force is in the direction of motion, simplest scenario. So if you've got a block and you're pushing it with a constant force over a period of space, then you just multiply force times distance, and that'll give you the work. Work will be in, if we're dealing with the metric system, it will be in Newton meters typically, and a Newton meter is the same thing as a joule. So if we are in the other system, the imperial system, and force is given in pounds and distance is given in feet, sometimes people say foot-pounds, sometimes they say pound-feet, whatever. Doesn't matter. One of those ways. Okay, so again, if force and distance are constant, simple. You just multiply the two together. If the force is at an angle, then you take the component of force that's in the direction of motion, using a sine or a cosine, to get the magnitude of the force that's in the direction of motion, and then you multiply those two together. We're not doing either of those cases, really. Those are both the simpler cases. So what we are dealing with is a variable force. Not a constant force at an angle or a constant force in the direction of motion, but we have a variable force. So the force is variable, and this is going to be our Riemann sum. We still are doing force times distance. Right? We still have force times distance. That is the core idea that we are going to keep. Force times distance is work. So the idea, though, is that if you zoom in on a super tiny interval, on a tiny, tiny interval, the force is essentially constant. And so if you're on a zoomed in super tiny interval, the force is essentially constant, so you can do force times distance. And then we let the width of each of those subintervals go to 0. The number of subintervals goes to infinity. We take the limit, and the Riemann sum becomes the definite integral. So there is our key formula, that work will be the integral of force if the force is variable. You can just multiply work is force times distance if you have a constant. But variable force, that's our new idea, which is probably not that new to many of you. So work is integral of force. The simplest problems with work and force are the springs. And the reason they are the simplest is that the force to compress or stretch a spring is a linear function. So the force is just some spring constant times the displacement, kx. So the k, the spring constant, every spring has its own spring constant depending on how stiff it is. And so quite frequently, we have to find the spring constant before we can do any sort of integration. We need to know what exactly is the force function for a particular spring. It's very similar to those problems that you did in college algebra and pre-calculus where you had radioactive isotopes. Every isotope has its own decay constant. Same idea. Every spring has its own spring constant, depending on how stiff the spring is. So, and we're going to use the same sort of horizontal orientation. Positive to the right, negative to the right. Excuse me. Positive to the right, negative to the left. So equilibrium is where the spring is just sitting there. The end of the spring is at 0. If we compress the spring, that means that the force is negative and the spring is going in the negative direction. So the displacement is going to be negative. Now, if the spring is stretched, then the force is positive and the displacement is going to be positive. That makes sense? Now, one thing that we're going to see with the spring, because it's kx, when you integrate it, you get x squared over 2. So we're going to see that the work done in compressing or the work done in stretching is the same. It's going to be a positive number. The work will be positive and equal to each other. If you compress it 2 centimeters or stretch it 2 centimeters, work will be the same. So there's some of that type of symmetry that you can use if you want to. So let's take a look at one. So here we have a spring. And they give us some information. They say that you need a force of 15 newtons to stretch it 0.25 meters. So that gives us a clue as to our spring constant. So we know that the force for a spring obeys Hooke's law, so we know that that's the force function. And they say, okay, well, if you apply a force of 15 newtons, you can either think of it as stretching it or compressing. It's not going to matter. If it goes in 0.25 or out 0.25, it takes 15 newtons. So that's going to be K times the displacement, which is 1/4 of a meter. So this tells us that our K value is 60. So that tells us that for this spring, the force function is 60 times x. That is the force function for this particular spring. All right. So part A. Assume the spring obeys Hooke's law. Find K. All right, we just did that. K is 60. Part B. How much work is required to compress the spring 0.2 from its equilibrium position? So work equals, we're starting at equilibrium, and if we compress, that means the spring is going to end up, the tip of the spring is going to end up a little bit more to the left. So it's going to end up at minus 0.2 meters. And again, if we did a stretch instead of a compress, we get the same answer. If we put 0.2 instead of minus 0.2, that's totally fine. That would give us the same answer. And then we put in our force function. We integrate with respect to x. That will be the work done. So we'll end up with 30x squared. From 0 to negative, that is 1/5. Let's write it as a fraction. And you can see right here, because of that square, whether you put a plus 1/5 or a minus 1/5, you're going to get the same work. So that's going to be 30 over 25. Divide out the 5. And we're dealing with newtons and meters, so you can call this a Newton meter, or you could use joule. Doesn't matter. Both are the same. And then in part C, they say, okay, now we've got this spring, we've got it compressed. How much additional work is required to stretch the spring 0.3 meters if it has already been stretched 0.25? So we're at the place where it's already been stretched 0.25, and we want to stretch it 0.3. How much is it required to stretch the spring 0.3 more meters? So it's at 0.25, and we want to compress it, or stretch at 0.3 more. So work will be, we're starting at 0.25, so it's been stretched to 0.25 meters, and we want to stretch at 0.3 more, which means we're going to go to where on the number line? 0.55 will be the end position. And then we still have the same forcing function, so that'll be our setup. This will give us the additional work. Integrate. Let's convert these things to fractions so that we don't have to deal with decimals. So 55 over 100, if you divide by 5, you're going to get 11/20. So plug in 11/20ths, and you square it, you get 121 over 400 minus 1 over 16. We just have to simplify that. Multiply top and bottom by 25 over here to get to 400. Yeah, Federico.
And if you knew that you were just stretching at 0.3 meters total, then would it change the answer if you made the limits of integration 0 to 0.3?
Yes, because the spring, it's going to get harder and harder to pull. You see it? Right, the first meter, or first centimeter, whatever units we're using, the first centimeter takes whatever it takes in terms of, the work done to do that. It's going to take more work to go the next centimeter, right? Each unit of length is going to take more and more work to stretch it. Yep. Which is why shock absorbers work. So multiplying top and bottom by 25 there, we end up with 30 multiplied by 121 minus 25, so that's 96 over 400. Those are both divisible by, let's see, we can wipe out a 0 first. And then both are divisible by 8, right? So 3 multiplied by 8 goes into 45 times 8 goes into there 12 times. So we'll get 36 divided by 5. This is work, so Newton meters or joules. Either one. Any questions on the spring? Spring, it's a pretty good first example because you can kind of visualize it pretty easily. Okay, so let's think about this one. So this says calculate the work required to stretch the following springs 0.4. So we're stretching 0.4 from equilibrium. So we're thinking about stretching it to the right. And these are two different springs. So different springs. So the first one gives us information just like the last one. It says, oh, 50 newtons to stretch at 1/10 of a meter. So for the first spring, it's going to look very, very similar to what we just did. So for part A, we are told, okay, we're using Hooke's law, so the forcing function says that it's going to take us, well, let's just write Hooke's law down first. So it says we're going to apply a force of 50 newtons, and that's going to stretch it 1/10 of a meter. So we know that for this spring in part A, our spring constant is 500 for this spring. So now we go back up here where it says, okay, calculate the work required to stretch the spring 0.4 from equilibrium. So the work is going to be 0 to 0.4, which is 2/5 from equilibrium, and we have a forcing function that's 500x dx. So that will be the setup. (250x squared), 0 to 2/5. So we end up with 250 multiplied by 4 over 25. And that is going to be 40 joules of work. Any issues with that one? So the second one is going to be a little bit kind of roundabout. So let's take a look at what they give us. So in any of these spring problems, it's really essential that we find this k. So we've seen that the one way they can present data so that we can find k is that they give us f and x. All right, now the second one, that's not what they do. The second one gives us data in a different way. They say it's going to take 2 joules of work to stretch it 1/10 from equilibrium. So we don't know f. Right? And the other one, they gave us f and x. So here's what we're going to do. So in part B, they say, oh, well, we know the work integral, right? So they say 2 joules of work to go from 0 to 1/10 of a meter. And we don't know k, but we know that it's got the form of kx. So that is the equation that will have just k as an unknown. And so we get to find k in a slightly roundabout way. So we're going to integrate. We're going to go from 0 to 1/10 of a meter. We can multiply both sides by 2 here. And then we have k multiplied by 1/10 squared is 1/100th. And so this tells us that k is 400 for this spring. So roundabout way to get to K. They give us information about work, not force. But then the rest of it's going to be kind of the same. So now we go to find the work done in moving it, was it to 0.4, so 0 to 2/5. And the force function for this spring is 400x. And that will give us 200x squared from 0 to 2/5, which will give us 200 multiplied by 4/25. That'll give us 32 joules. Okay, so when you're looking at that, is there any part of that you're not 100% sure of? You want to get the spring. The spring is the easiest of all these applications that we're going to look at. Any part of that? It's not making 100%? All right, let's go ahead. We're going to start to get into the harder applications now. So let's take our break now instead of trying to figure out the pumping problem while we're ready for a break. So let's take 10, and then we'll go to the next application. And with other work problems, we are going to have to worry about gravity because the force function is going to be, let's come here. The force function is going to be dealing with objects that are not just moving laterally, but stuff that's moving vertically, so gravity is going to come into play. So we know still that work is force times distance. That is our basic fact. That does not change. It's just that when we're dealing with the lateral motion of a spring, the force is kx. When we're dealing with something that's going up and down, force is given by mass times gravity, or mass times acceleration, Newton's law. So that's how it's going to be a little bit different. And whether we're lifting or pumping, whether we're lifting something out of a trough, or excuse me, whether we're pumping something out of a trough, like pumping water out, or whether we're lifting a book or any of that stuff, it's same formulas. If we're moving this direction, it's going to be the same formula. Now, the simplest scenario, again, is if we have a constant force over a constant distance. Like if you lift a block and you use a constant force to lift it, you don't have to do any integration. But if the force is variable, then you have to integrate. But if the force is constant, you can just multiply force times distance. Okay, so the context, we have a tank filled with water and we want to pump it out the top. That's our context. There's the formula. The formula is very gnarly looking. So what we are going to do in here is simplify the concept down to the essentials. So first off, let's make sure we understand what everything is in here. So the rho, that's density. Gravity, if we're dealing with meters, 9.8. This is the area of a cross-section. So that's area. This is distance traveled. And then you have your differential. So those are the things in there, and we need to make sense of those things. So what we are going to do is very similar to what we've done in the past. We are going to think of a representative slice of water, figure out how much work it takes to move that representative slice of water, to pump it or drain it or whatever. So you can drain stuff out of a tank or pump stuff out of the top with a pump. Work done is the same. It's just that the work is done by a pump instead of gravity. If you just drain it out of the bottom, gravity's doing the work. But if you pump it out the top, your pump is doing the work. So the basic idea again, so I've rewritten it down here. Here's our formula. And what we know is this. Here's couple of our basic ideas. Mass times gravity, that's force. So right here I have gravity. And density multiplied by volume gives mass. And these three quantities right here, or excuse me, these two quantities right here, area and distance, if you just think about the units and do your dimensional analysis, that area times distance gives you volume, right? You're going to have meters squared for this cross-sectional area, and then the distance that slice travels is also meters. So this right here is meters cubed right there. Density times volume gives us mass. So now we have mass times gravity. Mass times gravity is force. Force times distance is work. So the units all match perfectly. And the units for these problems is kind of how you keep your anchor into them. Now that still looks pretty gnarly. We need a simpler way to just be able to write that down every single time and write it down correctly. So here's what I want you to think about. We know that the volume of this slice is the cross-sectional area multiplied by the thickness, multiplied by the dy. So that's a volume right there, right? Our element is volume. So a representative slice is going to be volume. And we know how to find the volume of a disk. So, or the area of a disk and then multiply by the thickness. So here is what we are going to do. This is going to be the formula that we are going to use for work. ADD volume. That will always find the work when you're doing a pumping or a lifting problem. A is acceleration. D is density. Second D is distance traveled. And then we have our volume, our elemental volume. So that's the volume of a representative slice. So cross-section multiplied by dy. And that will always work. We're going to end up doing some other problems where we just have to find force, and our problem is going to be set up in a very similar way. We'll do ADD area. And let me just point out one thing. We'll get into the details of that. The units are all here. You can look at that and carefully analyze it. Force times distance gives work, right? Force times distance gives work. If we have area and we multiply by one other unit of distance, area becomes volume and we're back up here, right? Work is force times distance. Area multiplied by distance will get us back to volume. So if we're trying to find work, it's going to be ADD volume. If we want force, we're going to take away one unit of length to change volume to area, and then that's going to give us force instead of work. But we'll talk about the details of that as we get into it. So our key right now is ADD volume, and I'm going to come back to this problem in a second, and we'll talk about that one in a second. I want to do one that is going to reflect the idea of pumping water out of a tank, and then we'll go. The rope is done the same way, except that it's a special case which makes some things look a little different. So we'll do that one second. So here's what we have. Cylindrical tank, it's filled with water, height of 8 meters, radius of 2 meters, tank is full of water. This is always given. Density of water is given to be 1,000. Acceleration, we're going to deal with the metric system, 9.8. So here's what we do. So we say, okay, we are finding work. And the acronym that we're going to use is ADD volume. Very easy to remember. ADD, we're in math. ADD is add. Or attention deficit disorder if that is more meaningful to you. Whatever it is. And then volume. So ADD volume is going to give us the work done. So all we do is fill in the blanks. We have to know what they mean. Acceleration, density, distance. And when we talk about distance, the distance is how far does your representative slice travel to get out the top of the tank. So here, acceleration, 9.8, it's a constant. Density, it's water, it's constant density. So the first two are almost always 9.8 and 1,000. Now we look at our tank. Distance, so this is the first trickier one right here. So we look at a representative cross-section, So the cross section is an area. Then we add the thickness to get a representative slice. So when we say volume, we're talking about the volume of a very thin slice. We're not talking about the volume of the tank. We are talking about the volume of a representative slice in the setup. Now, this is pretty easy because every slice will have the same cross-sectional area. Right, so the area, cross-sectional area, is equal to pi r squared. So this is a cross-sectional area. Cross-sectional area is going to be equal to 4 pi. Right? No matter where you draw your representative cross-section, it's 4 pi. So volume, there's the cross-sectional area. We are integrating with respect to y, so we typically will use a dy. You could use a dx, does not matter. That is the volume. So when we say volume there, we mean the volume of a very thin slice. The thickness of our very thin slice is dy. That number part is the area, the cross-sectional area. Now with the cylinder, it's easy because it's constant. Right? Every cross-sectional area is 4 pi. If we have a cone or a trough, then that'll change. But that's it. That is a setup. What are the limits of integration? Where are these slices of water? They are from 0 to 8. So that will be the work done in pumping all the water right out of the top of the tank. Oh, I forgot the distance though. I didn't write the distance in. Why didn't I write the distance in? I gapped on. A little momentary lapse. And I told you that this is the trickiest piece right here. So let's get that piece. How far does this representative slice travel if this is the slice at y? It's going to travel how far? To get out the top? 8 minus y. Because you can draw your representative slice anywhere, right? And the distance it will travel is the total depth of the tank minus that. So 8 minus y. That's the hard part there. It's the 8 minus y. There we go. All right, so then pull out the constants. So almost every single time we're going to be pulling out this 9800. And then in this case, we also have a 4 and a pi. That all comes to the front. The limits of integration don't change. And the only variable part is the 8 minus y. Let me just write over here that this distance right there, that's 8 minus y. OK, so I'm going to just leave this as multiplication for a second. Maybe we'll get some cancellation. It goes 8y minus y squared divided by 2, 0 to 8. So plugging in the 8, looks like 64 minus 32. So that's 32. And we just have to multiply those together. So 9800 multiplied by 4 multiplied by 32. So this will give us that. So what is that? Looks like 1,254,400 times pi joules of work.
Not much, right?
Right. It's a lot of pi. So there's our basic work problem for pumping. So ADD volume, and by volume we mean volume of a slice.
And this is only defined like volume different objects?
So in this particular problem, we're finding the work to empty a tank, to pump all the, whatever it is, water, maybe it's oil, whatever it is. So this was for a cylindrical tank. Let's do one that's not cylindrical and see how it can get a little bit more complicated. Because when it's a cylinder, it actually feels pretty easy, right? Because it's distance is the hardest part. cross-sectional area of a cylinder. And this is pi r squared. So let's do one that's a little more complicated.
Will that acceleration value ever be negative?
No. Yeah, we'll always use positive 9.8.
Okay.
Okay, so this one a little more complicated. We've got a trough that's got a semicircular profile. So let's draw that profile over here. And my habit is to put a coordinate system based on the literal geometry. Because it's a semicircle, some people are going to be inclined to put the coordinate system so that the center, 0, 0, is right there. If this is a semicircle. Totally fine. But if I just like to have it be all above the x-axis. If you want the center at the origin, that's fine. You just have to remember when you do a vertical element, it's upper minus lower, those kind of things. So doesn't matter though. Okay, so this says that this circle is going to be radius 1/4. So let's write down the equation for this part of the circle. So this distance is 1/4 right there. Then this is going to be x squared plus y minus 1/4 squared equals, what would be the right-hand side?
Integrated
1/16. It's this. Radius is 1/4. Square the radius to get the right-hand side. Now, when we draw our element, over here, there is my element. Constant, right there, cross, constant height. If we draw it over here, let's draw the corresponding element here. Then we extend it, right? We extend it the length of the trough. So we're imagining a rectangle as our representative cross section. And if we multiply by dy, our representative slice. Right? So representative slice is going to be a little rectangular box. It's a cross section of a rectangle with a little thickness, making it a rectangular box, a very thin one. Okay, so this is a horizontal element. We are going to need to know, right, that's the width of our rectangle. We're going to need to know that distance across. That's an x distance. That means when we look at our equation here, we want to write it as x values. So we're going to isolate the x. So this is going to be x equals plus or minus the square root of 1/16 minus, then we're going to FOIL that business out. So we're going to have y squared. And then it's this times 1 times 2. So that's going to be 1/2 y plus 1/16. Everybody okay with that? Foiling. And this tells us then that the right edge is the positive square root. The 16ths are going to cancel when we distribute the minus sign. So we're going to have negative y squared plus 1/2 y. So that's the right half. The left half is going to be the negative square root. Any questions on that algebra piece? So we're getting the right and left semicircles by solving for x. The right one's the positive one, the left one's the negative one. So I am going to just put a W here to represent the width across there. So I'm going to call that W, that dimension across there, that chord that's going across that semicircle. Can you tell me what W is equal to? Did you just say this? Or was I hearing what I wanted to hear? Is that what you said? Right minus the left. So square root minus minus square root gives 2 square roots. So that's how you could think of it, right minus left. You could also say hey, there's symmetry here. This is measuring exactly half of W. So you could just take that and double it also. So two ways. You could say it's right minus left, which gives you root minus minus root, which is 2 root. Or you could say, oh, that full distance is literally just twice that. So you could just find the right side and double it. Same thing. OK, so that then tells us the following. So let's go ahead and set up our work then. So work is going to be the integral of ADD volume. So that's our acronym that's going to give us insight into how to set this up. So we're going to have work equals, again, we're dealing with water. So let's make sure we have everything right here. So it's acceleration, it's density, and distance traveled by a representative slice. So if we look here, we are going to call this the representative slice at a height of y. Okay. Anytime we draw a horizontal element, we say it's at y. Anytime we draw a vertical element, we say it's at x. So representative slice at y, representative cross section at y. The distance traveled then is right here. This is the second d. That, if we're pumping it right out of the top of the trough, what's that distance going to be?
0.25 minus y.
Say that again?
0.25.
Yes, 0.25 minus y. Yes. So 1/4 minus y. That is our distance. 1/4 minus y. Does everybody see that? So the total distance from the bottom of the tank to the top is 1/4. And if we have a slice at height y, the distance traveled is the 1/4 minus the height of y. That'll give us the, this complementary distance. Y is this distance. That distance is going to be 1/4 minus y. All right, so that's usually the hard part, is getting the distance right. OK, so then now we have to multiply by volume. Bless you. Volume. And when we say volume, we don't mean the volume of the trough. We mean the volume of a representative slice. A representative slice is a rectangle with this area. So there's the area. This is the area of our cross section. And how do we turn our cross section into a slice?
Add another dimension.
Put another dimension, put a dy. Now we have volume. So this is volume. So volume in all these cases is going to be area times thickness. That'll create volume.
Isn't the 2 root just the one section? Did we multiply it by the 3 meters of the tank?
Oh, we didn't get area yet. This is just length. Yeah, thank you. Yeah, this is just the width across. We still do have to put in a 3 for that dimension. Yeah, so right here we only have meters. And then we have to multiply by the length of the trough, which is 3. Thank you. Ooh, space that part out. So times 3 times dy. Yeah, there we go. Yeah, that square root thing looked like it was so big that it was area, but it was just length. It's just the width across the face.
Okay.
And then the 3 gives us the depth, or the distance in to the back. And then the thickness is the dy.
One more time, the root minus y squared plus 1/2 y, is that the vertical?
This is the distance from left edge to right
Okay.
edge. That's what W is. So that's one side of the rectangle. It's the front side of the rectangle. And then we've got the depth side of the rectangle is 3.
Yeah, and then our is
Exactly. So we've got width right there. We've got length right there. And then we have thickness right there. Yeah. 3 dimensions for a rectangular box. OK. And then our limits of integration, what do you think? Zero to 1/4. So the way we set it up. Now, if you set it up with the circle centered at the origin, you would be going from -1/4 to 0. Because if you put your origin up here, then this curved part of the trough would be below your x-axis, so then you'd be going from -1/4 to 0, which that's the part I don't like doing it that way. I'd rather go from 0 to up to the top. So 0 to 1/4. All right, there we have our setup. So a little more complicated for sure. So let's get all our constants out in front. Notice no pi's in here, right? Our representative slice was a rectangle. So no pi. And when we had the cylinder, so our cross section was a circle, then we had a pi. So we're going to get the 9800 multiplied by, looks like a 6 is going to come out. Now, if we want to be clever, which we do not have to be, when you look to the integration piece of this, substitution is going to be the natural first candidate because you've got something inside of a root, you've got something outside of the root. When you look inside the root, what is the derivative there? Minus 2y plus 1/2. If we take this 2, and instead of bringing it all the way to the front, we could just share it with this factor if we wanted. Right? The associative law of multiplication, if you have a times b times c, you can multiply a times c and then multiply that by b, or you can multiply in any order. So we could be kind of proactive, if you will, and we'll pull out the 3, and let's leave that in there for a moment and just see what happens. So when we distribute that 2 there, we're going to get 1/2 minus 2y. And then we have our square root. And then the dy. So we pulled all the constants out by the 2, except the 2, and we shared the 2 with that distance factor. And now watch. When we do our substitution, when we say u is going to be minus y squared plus 1/2 y, and of course, if you didn't see that and you pulled the 2 all the way to the front, it's not going to matter. You're just going to have a division by 2 built into this part. And now we see that, oh, that matches exactly right here. 1/2 minus 2y, there's 1/2 minus 2y. So those match. Okay, so 9800 multiplied by 3. We can multiply that out. Usually I'll just wait because sometimes we're going to end up with a denominator that will have a common factor. So this integral then becomes, we have the square root of u. That was this main part. And isn't the whole rest of it just du? 1/2 minus 2y times dy, that is du. And let's convert our limits because it's easy in this case. So first we have a lower limit of y equals 0. Plug that in here, we get u equals 0. We have an upper limit of a 4th. Plug that in here, and we'll have minus 1/16 plus an 1/8. Minus 1/16 plus an 1/8 is positive 1/16. So there is our final integral. So we'll end up integrating that with the power rule. So we'll have u to the 1/2. Add 1, we get u to the 3/2. Multiplied by 2/3. And that's going to go from 0 to 1/16. And so in this case, we see that, oh yeah, there was no point in multiplying the 3 across because they're just going to cancel anyway. And what are we left with then? So we have 9800 multiplied by 2 multiplied by square root of 16. Excuse me, square root of 1/16 is 1/4. So we have 1/4, but then it's cubed. So in the denominator, we're going to have a 4 times 4 times 4, which is 64. So we're going to have that. And we can simplify that. That's pretty pretty reasonable. So 9,800 divided by 32. That's going to give, and let's see if I want to change that to a fraction. That's going to be 1,225 over 4 joules. So let's slide back up to the setup for a minute, because this is definitely more complicated than the cylinder. Now that you've thought about it for some minutes, is there any part of that that you want to talk more about? The common mistake is when we look at our volume, the common mistake is to feel like you're trying to make the volume of the whole trough instead of the volume of a little slice. So we need to know what our region looks like. Our region was a rectangle, so we had to do width times length times thickness, versus the last one, which was area times thickness. So this is the volume of a very thin rectangular box. All right, let's try one more complicated looking one, a cone. So there's a cone. So let's see if we can look at a representative cross section is right there. And if we add thickness to it, then we get a representative slice. And we're going to say that this is at a height of y. What does that immediately tell us about this distance if we're pumping out the top?
Y minus 6.
Close.
6 minus y.
6 minus y.
Oh,
6 minus y. Right, because the full distance is 6. This height here is y, so this complementary distance is going to be 6 minus y. Okay. So we know that we're going to need the area of this cross section right there. Okay, area, that's going to be a disk, so we're going to need that radius value. So if we flatten our cone into 2 dimensions, we have a line as the right boundary. Right? You can imagine this line right there. If we were just to flatten it out, then we have a line right there. And all we need to know is the equation of that line. That r value will be represented as an x value in that equation. So if we find the equation of this line and solve for x, that gives us the radius. Because this radius is measuring the distance from the center over to that diagonal line. So what is the equation of that diagonal line? Well, the way I'm drawing it, this is the origin right down there. We're just imagining it going right through the origin, and it's a line. So it's y equals mx. So y equals mx. Slope, the rise, 6. The run, 1.5 times x. That is the equation of that line. Rise over run. Up 6 over 1.5. And that is 4x, correct? Slope there is 4. Everyone agree? Okay, so should I leave it as y equals 4x, or should we rewrite it? Rewrite it. So we're going to write it as x equals y divided by 4. So that is the radius. That tells us the radius at a height of y. So if y is 0, the radius is 0. If we're way up here at the top, if we plug in a 6, when the y is 6, the radius is 1.5. So this tells us the radius at every y value between 0 and 6. So that allows us then to find the area of a disk in here. So it's going to be pi times the radius squared. That is the area of the disk. So pi y squared over 16. So that's the cross-sectional area. And if we want to make it a slice, we multiply that by dy. Okay, so let's set up our generic formula. Work is the integral of ADD volume. So this is going to be 9.8 times 1,000. We can just pull that to the front because that happens almost every single time. So that's the first two letters. And then what goes in for this d here for distance? 6 minus y. So that goes in here, 6 minus y. That's this one. 6 minus y. And now we have to put in the volume of a slice, a representative slice. Volume is the area of the cross-section multiplied by the thickness. So the area of our cross-section, pi y squared over 16, multiplied by its thickness, which we're going to say is dy. And this is going to go from 0 up to 6, since it's full. And that'll be our setup. What if the tank was only filled to 4 meters? The tank still was 6 meters tall. If this only went up to, if the water level only went up to 4 meters and we were going to empty that all out, what would change? The distance traveled is actually not going to change. It's still going to be 6 minus y. It's just that the y's are not from 0 to 6. They're only from 0 to 4. So the only thing that would change if the water level was only up to 4 would be 0 to 4. Your limits of integration always physically reflect exactly where the water is. Now, if the water level was here, but then we had, let's suppose we had a 2-meter pipe up here and we were going to pump it out 2 meters above the tank. Then, and let's suppose the water is still filled 0 to 6. So it's filled 0 to 6, but we have an extra 2 meters of pipe. What is going to change? 8 minus y. The only thing that would change is the distance traveled. We still physically would have slices of water from 0 to 6. It's just that the distance they would travel the 6 minus y if we wanted to go to here, but if we wanted to go out up here, it would be 8 minus y. So that the distance traveled for the lowest slice would be 8. The distance traveled for the upper slice would be 2. So it would be 8 minus y instead of 6 minus y. Okay, let's pop the constants out to the front here. So we're going to end up with 9,800 times pi divided by 16. And 9,800 pi 16. And then we'll distribute the y squared, giving us 6y squared minus y cubed times dy. Okay, so integration, not too bad. We'll deal with these constants in a moment. So this will be, add 1, we get a 3, so we're going to get 2y cubed minus y to the 4th divided by 4, 0 to 6. So let's put a W out here. Okay, plugging in 0 gives nothing. Plugging in 6, we have 6 times 6 is 36, times 6 is 216, times 2 is 512. No, 216, 432.
Yeah.
432, thank you. And then plugging in 6 over there, we're going to have 6 cubed again, so that's a 216. And then the 4th 6 is going to cancel in the denominator. So we're going to have a 216, and instead of a 6, we're going to make that a 3 and a 2, but then we're going to make that a 1 and a 108, something like that. And then we'll just multiply all that stuff together. So 432 minus 108 times 3. So that's going to be 108 minus 432. I'll put in an intermediate thing here. So I'm getting 324 for that. Divide that by 16. Multiply that by 9,800.
I think you forgot to add 432.
Say that again?
It's 432 minus 324 as well.
Oh, is this part 324 there?
Yeah.
Oh, I see. Thank you. And what does that turn into?
108.
Oh, just 108. Okay. All right. And anyone get the final all the way?
66,150 pi.
66,150
And 50 pi.
pi. Joules of work. Perfect. Yeah. I have no idea how much work that is. I don't have any good sense for, no intuition. Okay, so the trough ones, these tank problems, are super visual. You know, and you have to draw a picture, you have to figure out your distances and your cross sections. Very similar to what we've been doing with the other volumes. Let me go to here first, and I've got a little note here that says, when dealing with one-dimensional density, there is no area factor. So if we think about a chain or a rope coming down, when we do our cross section, right, we're not in, there's no area. We are thinking of it as just a wire or a line, something that's one-dimensional. So we just don't have this one factor. So how are we going to modify that in our concept? So let's see. Let's see how we're going to do that. So this is what we're going to do. So instead of ADD volume, if we are in a one-dimensional density situation, we're taking away that cross-sectional area. So instead of volume, we just have length. So instead of a representative volume for our cross-section, we're just going to have a representative length, which is just dy. So remember that anything in these parentheses is going to have a differential in it. So this is area. Over here, we're thinking of this as area multiplied by dy. Here, all we're left with is the dy if we take away the area. So if we have our rope and we're doing a cross section, it's just a point, and then we add the thickness to it, which is going to give us the dy. So that is going to be our setup. So let's see if we can manage this here. So first off, we're dealing with a rope which they've given us a diameter which makes you feel like you should have cross-sectional area. But what we notice immediately here with our density is that they've given us a 1D density. They gave us grams per meter, not grams per meter cubed. So if they gave us grams per meter cubed, then of course the diameter of the rope is going to be important. But they gave us density as one-dimensional. So that's a 1D setup right there. It's not per meter cubed. So that means that the diameter of the rope is not necessary. Okay, so next, let's notice the units. So the density is 55 grams per meter, but we want kilograms and meters together. If we were doing grams, we'd want centimeters, but we want newtons and joules, so we want that to be a kg. How many grams in a kg? 1,000. So we're going to just do this conversion. So we're going to have 55 over 1,000. And this will then be kilograms per meter. And 5 goes into there 11 times, into there 200 times. So that's going to be our density. So that's the density of the rope, uniform density. So our work done, instead of ADD volume, it's going to be ADD length. Everything else is the same, means the same thing. Acceleration, density, distance. So acceleration, that doesn't change. It's the acceleration due to gravity. The density we just found, that's 11 over 200. And now distance. Let's imagine our scenario. So we've got a 60-meter rope. It's hanging freely from a ledge. So here's our rope, 60 meters. Let's pick a representative element of rope. That's right there. I'm going to say that it's at height y. How far does that representative element of rope have to travel? 60 minus y. That's the distance it's going to travel. So that is what the d here means. So that d is distance traveled by your element, whether it's a disc or a segment of rope or whatever, a rectangle. And then length. That length is nothing more than the differential. It's the thickness of that little element of rope. You've got a speck of rope, and then you make it into a little thickness. And how about our limits of integration? 0 to 60. We have segments of rope all the way from 0 up to 60. And so that will be what we get. So 9.8 multiplied by 11 over 200. This is integrating to 60y minus y squared over 2 from 0 to 60. 0 does nothing. So plugging in 60, we get 3,600 minus 1,800, which is 1,800. We can cancel a little bit here. That's going to all turn into a 9. And then we multiply that together. 9.8 times 99. So I'm getting 970.2, and if I convert it, 4851 over 5. So what somebody else gets? Yeah. Okay, good, thank you. So the big difference here is that volume becomes just length. So it tremendously simplifies it, but it's super easy to think that there should be more. That there should be more than just the dy, but there isn't. Just the dy. All right, let's try. Oh, did that one have, oh, this one has the block on it. So let's do this one. So here we have a 30-meter chain hanging vertically from a winch. There's no friction system in the system. Chain has that density. That density, again, like we just had on the last one, that's a 1D setup. So as soon as we see that the density provided is one-dimensional, we know that it's ADD length instead of ADD volume. So we know that our work is going to be ADD length because it's one-dimensional. Okay, so let's start filling in blanks. 9.8, that's gravity. Density, they gave us density to be 5 kg per meter, so that's the first two. Acceleration, density, now distance. So let's draw a picture if we need to. There's, okay, so we've got this, I guess we don't need, so we've got our chain hanging down and it's attached to a winch. Looks like a balloon, okay. And it's 30 meters. Okay, and this, we're going to pick a representative piece of chain, a link of chain, and that link of chain is going to be at a height of y. So how far does that travel then? 30 minus y. That's going to be how far it travels. I don't like putting that little minus there. That makes it look weird. So we've got our representative link of chain at a height of y. So this distance right here is y. From there to there is y. So then it's going to travel 30 minus y. That link is going to travel 30 minus y. And then all we put's a dy. That's it. That's the length. It's the length of a little segment of rope, dy. Limits of integration? 0 to 30. So how much work is, okay, that? So this is A. Okay, so we can pull out the 9.8 and the 5. So that's, let's see. What is 9.8 times 5? I should be able to do that. 40 what? What is it?
49?
That's what I was going to say, but that doesn't feel right. But 49, that's right?
Yeah.
Because it's 10 times, it's 50 minus 1. Yeah, because 0.2 times 5 is 1. So 50 minus 1. Okay. Just didn't feel right. So then we have 30y minus y squared over 2, 0 to 30. Plugging in the 30 gives 30 times 30, which is 900, minus 30 times 30 is 900 divided by 2 is 450. So 49 multiplied by 450. 49 times 450. And 22,050?
Yep.
And that's joules. So now, we're going to strap a block onto the bottom of the rope. So we found the work done to coil up the 30 meters of rope. Now if we add a block onto it, what's going to happen? So it says how much work is required to wind the chain onto the cylinder if a 50 kg block is attached to the end of the chain. We can treat it like two separate problems. We can imagine the work done in winding the chain up, which we just found, and then we can find the work in just lifting a block 30 meters. So for part B, the work just for the block is going to be mgh. It's going to be the mass of the block multiplied by gravity multiplied by the distance traveled. Something's wrong there.
50.
What's the mass of the block? 50, thank you. So that's going to be the work done in lifting the block. That's how much work it's going to take to lift the block 30 meters. So all we have to do is multiply that and then add it to the other one. So we are going to have 50 multiplied by 9.8. So this is going to be 14,700 joules. And then our total will be whatever the sum of those two is, plus. So 36,750 total. Any piece of that you want to ask about? Okay. Next. This is weird. I think we're to the weird piece. Okay. Here's something weird. So, all the things we've been doing so far with the ropes and chains, the entire rope or the entire chain has been lifted to whatever the top is, onto the winch or onto the edge of a cliff. So let's suppose we have a 40-meter chain density, let's just make it 1 kg per meter. It's hanging from a winch. How much work is required to wind it halfway up? So this is done like the typical way. There's 2 ways to approach it. You can approach it with what I'm referring to as the reality method, or you can approach it with a initial versus final state perspective. Let's first look at the reality method. So the reality method, if we're going to wind it up halfway, here's the top half of the chain, 20 meters. Here's the bottom half of the chain, the lower 20 meters. When you wind it up, it ends up looking like this. Right? The orange ones get wound all the way to the top. And so this is left dangling, which acts just like a block. So we could say, oh, we could imagine the lower 20 being consolidated into a block of whatever its mass is. And it would look like that to start, and it would look like that to finish. It's just like the problem we just did. Okay, so if we were going to do it that way, there's the reality method here. So the MGH, this is the block. And it's just a dangling cable. And then this part, we'll do the ADD length. And we are winding literally from 20 to 40, right? These are the segments of chain that are being wound onto the winch. So that's probably the more intuitive way to do it. But if you look in the answer key, so that's the way I did it the first time I saw the problem. That was the way that made sense to me. They had that as the answer. And I was like, whoa, that's looking a lot simpler than the other one. So let's think about this initial versus final state perspective. So what we can imagine, so here's the initial state, and we need half the chain to end up on top. So what you can imagine is this, the lower section ending up on top, even though physically, of course, that can't happen. But the final state is that we need 20 meters dangling. So instead of zipping the top half up, we can imagine, even though, again, it's physically not possible, we can imagine zipping the bottom half up to the top. So if we zip the bottom half up to the top, then we're focusing on the links from 0 to 20. And then we do ADD length, and we will get the exact same answer as we will get here. It's not super intuitive to me. Maybe it is to some of you physics people. But that is the quick and dirty way to do it, is to imagine these going through a little wormhole and ending up there, and that will give us the same answer. So when we look at this, does this method make sense to you, the reality method, where we're physically moving these links from 20 to 40, and then we're dragging this extra, essentially a block along? That seems very intuitive based on what we've done so far. But you should work them out, work both of them out, and see that you get the same thing. It's a little mind-blowing to me, but it's physics, man. Physics is mind-blowing, right? Math is very deliberate. Physics is a little fishy. Okay, so let's talk about the final piece of 6-7. We probably won't have time to do a full example, but we can at least talk about it. So hydrostatic pressure is interesting. When you go underwater, there is the same amount of force being applied to every point of view, right? You're getting it from all directions. So hydrostatic pressure has this weird thing that it pushes in all directions simultaneously with the same force. So here is an interesting question. So we're going to be dealing with dam walls. So let's just suppose that's a dam, and we've got water behind it. So we've got this water, and it's in a canyon or whatever, and the water is pushing on the face of that dam. And we're going to want to know what is the cumulative force pushing on that dam wall, so that we know how thick to build it. Right? So my first question to you is, let's suppose that we have 100 feet of water directly behind the dam. So have that in your mind. And then let's extend it and say, hey man, we're building this dam. Let's go for broke. Let's add more water behind the dam wall. So instead of 100 feet of water pressing on it, we have 200 feet of water pressing on it. The question is, how much more force is being applied to that dam? Any idea? How much more force? Anyone have a guess?
Twice the number.
Okay, we hear twice. Seems like a reasonable guess. Anyone know the answer?
Okay, maybe,
Yeah.
It'd be squared.
It's a reasonable guess. The answer is 0. The answer is 0. Because with hydrostatic pressure, it's pushing in all directions simultaneously. So you can kind of think of, if you think of adjacent molecules of water, they're kind of canceling each other out. If you have 1 inch of water behind the dam or 100 miles, the same force is acting on that wall. Right? That just doesn't make any intuitive sense with our experience in everyday life. So what you should do in D2L, I have those weekly videos just for, they're fun. They're fun videos. There's 2 on hydrostatic pressure. You should watch those 2 because it is the most unintuitive concept that I've experienced with the kind of physics stuff that we see in Calc 3 and Physics 2. Like, that just seems so unintuitive to me. And those 2 videos do a really good job of kind of showing some good physical examples of how hydrostatic pressure works. Because it's, in my experience, I would say it's unintuitive that that's going to be the case. So that's why we're going to build our dams with such huge reservoirs of water, because you might as well. You're not adding any extra work here. Now, if they're doing a project up, the biggest Boulder County up at Gross Reservoir right now is increasing Gross Reservoir, which is the water supply for Denver. They're increasing it by something like 150 feet. They're increasing the depth of the water massively. And so right now they're up there building this dam that now they've got to thicken it at the bottom, because now if you add more depth, that changes everything when you add more depth. When you add more depth, then the wall's got to be thicker at the bottom. So it's like one of the hugest public works projects that we've had in this area our entire lives. It's huge. It's going to take like years. But it's going to be, I think it's going to be like the 2nd biggest body of water in Colorado once they're done with it, or something crazy. It's going to be a huge recreation area. But Denver needs the water. All right, well, let's stop there, and we will pick it up on 2 days from now.
You're talking about this section, you mentioned that only the test, or just that specific problem you're talking about? Or
Oh, no, I didn't say what did you say?
There was something, it was like one of the first things we did. Oh, this won't be on the test, but I was assuming that it was just that.
Oh, that one specific thing won't be on the test, and that's where we're just finding the mass of, that thing. That's just
what I thought, and I was like,
yeah.
I just want to.
Yeah, just question. Not all 6-7.
Right.
Just that finding the mass of a rock.
Maybe.
The concept's important, integrating density.
It's like a third.
Yeah. Anyone have questions? Stick around. I'm going nowhere.
Could you get an email about my.
Oh, I forgot to take roll. Oh, well. And you are Elijah?
I'm Elijah.
Yes, I've got that.
Okay,
So,
awesome, thank you.
testing center,
Yeah.
1.5.
1.5.
And you're just going to email me at least 48 hours ahead of time so I make sure that it's on my list to put the test up there. Yeah.
Thank you.
Yeah, sorry for not taking
No.
You want to take a test?
I just wanted to make sure that everything.
Yes, so you have to make your appointment with testing center.
Gotcha.
So you'll make your appointment and this is still the plan, is to take it on this Friday.
Yep.
All right? We'll do it.
Thank you.
It will be there waiting for you.
I don't want to confuse myself by focusing